Okay, so this is a slide from the last hour. Okay, let's move on. Okay, so this is a dynamic. This is one of dynamic scenes, and say we want to interpret this scene. So all maybe what we've seen before. So I would say that it would have issues. The methods which we've seen before, it would be complicated to analyze such a dynamic scene because we have many problems. So what are the problems? So what are the common methods first? So first, maybe if you want to do shape analysis, so you would need to do some segmentation. So if you would need to track, so maybe the previous methods which we've seen, so tracking the person, analyzing the motion of the person. So again, tracking would have issues in the scene because of many things. So what are the problems? So for segmentation, we have a complex and changing background. So we just cannot segment the scene. So can you see? Can you see here something? It's maybe hard. Because the background is dynamic, everything is moving, so it's basically impossible to segment the scene. So why actually does it fail? Because usually segmentation methods, they have some model about the background. So they usually assume that the background is something static, big. So everything which is not moving as the background, this is a foreground. Okay, this is a typical assumption for segmentation. So here it just fails. Okay, so the assumption for tracking is that things are continuous over time. Okay, so that you have appearance. Maybe you have some model of appearance, how it changes. Maybe so the shape of a person and so on. But either you have a model or so assumptions that you know enough about the foreground so you can model it appropriately. Otherwise, the tracking will fail. Okay, so both two things are problematic because in realistic scenes like this, so it's hard to assume anything about the background, and it's also hard to assume things about the evolution of, say, person or other things over time, because the appearance may change drastically for the reasons which are hard to model. So all this, so if we still want to understand this scene, so maybe a reasonable way to deal with these problems is not to do any assumptions about the background of the scene and also about the temporal continuity of the signal. Okay, so we don't want to do any global assumptions in space, neither in time. Okay. So and now if you don't do any these global assumptions, so maybe what is left is just to look at local information, so which is available in the video. So say now, okay, we are back to simple sequences for illustrative persons, illustrative reasons. So if you just look at these simple sequences, if you take space-time cut on these sequences, and so again, this is not the data which we are going to analyze. This is just to visualize how the data looks like if we just put the threshold surface around the silhouette and stack the silhouettes in time. So that's how it looks like. And now we see already this with this visualization. So it's this shape, if you call this a shape in space-time, this looks very differently, not only in global, but also in local. So if you think of analyzing some local properties of these parts in space-time, so they seem to be quite informative. So of course, going this thinking is inspired by analysis of images. So in still images, maybe you are familiar with visual words, representations, where you can first subdivide an image into patches. There are many different methods to do this, and then cluster the appearance of different patches so that you not necessarily get semantically meaningful things, but quite often you get something which is quite consistent. So you get parts of airplanes and so on. Okay, and with this type of representation, so it has practically proven to be very useful for recognition. So if applying now similar strategy to video, so what we can do, we can think of now looking at local spatial-temporal neighborhoods around some particular points, or maybe even just taking all the spatial-temporal patches in the video. And now, as I said, so we are not looking at this green surface, but looking at spatial-temporal so representation, the pixels over space and time, so we can get the 3D patches. And now these 3D patches, which extracted here and here, they're really different. So imagine we can also, and similar to this type of presentation, so we can imagine we can build some classifier which just works on local patches and would be able to discriminate between these two actions. Okay, and the goal, of course, is to move on to more complex videos. So here are still a simple citation, but in more complex videos where we would have a complex background and so on. So if we are just reasoning about the local information, we should be less dependent on this variation which happens around the person in the whole scene. Fine. So this is okay. This is one possible way how to extract first the points or the spatial-temporal neighborhoods. So this is just one way, and there can be other ways. So the reasoning here is similar to Harris point detection. So how many of you know Harris point detection? Okay, quite many. So this is really very similar. So in the Harris point detection, so if you're familiar, so you have a 2x2 matrix which you analyze. And what is this matrix? Actually, this part of the matrix is the same matrix which we've seen in the previous hour for optic flow estimation. So it has many different names. So one name is so what is it called? This second moment matrix. Yes, here it is. So basically, it's a covariant matrix. So if you assume that the gradients have a zero mean, then so this matrix would be the covariance matrix of gradients in a local neighborhood of an image. Now, if you extend it to a video, so if you have a spatial-temporal neighborhood, so the matrix become 3x3. So you just measure the gradient vectors are 3D. So this is a covariance matrix measuring 3D. Okay, so what Harris standard 2D Harris point detector does, so it tries to find points which have both eigenvalues large, eigenvalues of this matrix large. So why? Because the typical corners they would correspond to points where we have a gradient direction to different, well, in not just in one direction, but in many different directions. So that's, for example, why optical flow estimation would also work on corners, because we have gradients pointing in different directions. Okay, so similar thinking here. So if we have a if the rank of this matrix is 3, so this indicates some interesting space-time structure, which is maybe some corner which moves not only with constant direction, but also, so it has some significance in time, as it has some change in the motion in time. Okay, so maybe just simpler to show this with videos. Okay, so the form of the saliency function is like this. So it's about trace and determinant of this matrix. And so what basically, so okay, I'm not going to details of this, but this function fires, if we maximize this function over space and time, then so it fires at this, for example, for the examples here in the videos, it will fire on blue points here. And so can you guess what, so is it clear what this shows? So basically, so this video and this picture, they correspond, right? So this is a corner which moves up and down. And so the firing, so this is a time dimension, this is X and Y. And the firing is in particular point in time and in space, because it has a sort of a space-time corner, basically. So it has a gradient, space-time gradients have different direction. Okay, and the same things happens here. So this is a sort of example where some structure hits a wall or two structures merges, so we get these events. Okay. So it's not that other events are not interesting, but these are some distinct events which could be interesting for recognition. And now, if now for real sequences, so we can get something like this, firings, and for here's a football heading the ball, and so we get, so on the space-time slice, we can get a event which corresponds really to a space-time corner. Okay. So one can, as for other interests, so spatial interest point detectors, so one can make it scale invariant or scale covariant, so that if we have a camera zoom, if we have a variation in terms of the scale in spatial scale, so we can detect these points which so see they follow the scale. So why is it good? Because if we are going to compute some descriptors at this point, so we not just need the location, but we also need the size of the patch. Okay, so to make really two descriptors in different videos to correspond, not the corresponding central location is not enough. You also want to have the size of patches to correspond. Okay, so if you want to match this leg to this leg, then obviously we need to adapt the size of the descriptor. So in space-time, similar. So we also need to adapt the. We may want to adapt the temporal size of the descriptor. So what is temporal size? So here is a hand waving with different frequencies, and we see that the size of the temporal size of the blobs, detected blobs, it's adapted to the frequency of the event. Fine. Okay, so these are points which are detected for different types of actions. So here, as we've seen, this is boxing, this is hand waving, this is you can guess probably what this is. What is this? Walking, yes. Okay, and now so we reduce the representation of these actions to a collection of patches. So this is a way to represent videos, and so once we collected the patches, we also want to describe them. So one description would be just to collect the pixels and maybe do some contrast normalization. So it turns out practically better to make descriptors in terms of histograms. So as you well know, the SIFT descriptor is a histogram of gradients. So here we experimented with many different descriptors, and these are the ones which seems to work best. So it could be gradients of histograms of gradients, so spatial gradient orientation, and histograms of optical flow. So we collect the optical flow in space-time neighborhoods and quantize them into very coarse quantization. So just 4 bins of the for the upward, downward, left-right motion or no motion. This is the histogram, and also in a SIFT manner. So if this is the patch, so we divide it into a few blocks. Why is this useful? Because it preserves some spatial or temporal information, but is not committed to a very precise location. Okay. So here is one illustration of what the method is doing on simple sequences, and this actually you will experiment with this example in the practical exercise in a short. So what happens here? So we first extract the points, and so we can we extract the points. We extract the patches and apply some descriptors to patches. We can next do standard k-means clustering on these patches and say extract the 4 clusters which are most common. And because the action is periodic, so the most common will correspond to repetitive, small repetitive structures. So if we just select the patches which correspond to the first 4 clusters, so we remove the noise, and also we can get the kind of semantical, although there is no in k-means, it's not a semantical method, but it does cluster similar events, local events together, so we can have a nice representation. And now if we if we keep this dictionary, okay, so if we keep these 4 clusters and we apply it now to a different sequence which has not been seen during the construction of this dictionary, so we can still recover the same type of events in the new video. Okay, and now so here we start to see advantage of this method is because we have cars and things moving on the background, and the method is invariant to this type of variations. So here is another visualization why this approach could be useful. So here we have many videos, and we just try to do nearest neighbor matching between descriptors, so without taking into account any global information, so just based on the local descriptors. And so as you see here, there are quite meaningful matches here, so between different people in different situations. So we get quite good matches. So this would indicate that if building on top of this representation, it should be useful. So here are some mismatches, I think. Yes. So here are 2 mismatches. One is for hand and a foot, and you can imagine why this is mismatching, because the motion and the shape are similar, and just local information is not enough for correct matches. So here is also here. I think this is boxing, and this is maybe like hand clapping. So it's fine. So this is the bag of words pipeline, which you probably many of you have seen at some point. So this is now standard for image classification and for video classification. So for video we collect again the patches, and so these are the patches. We describe them with some descriptors, for example, Hof descriptors, and so now vocabulary. So here it's just 4 clusters, but usually it's much larger. So typically it's for classification tasks we use about 1,000 or like up to 10,000 maybe visual words. So around 5,000 it stops changing much. So and then so just counting the number of patches of each type in the video. So gives a histogram. Histogram is a fixed length description vector which you can feed into your favorite classifier and get the classification result. So that's the pipeline. Okay, so that's one data set which has been quite popular for a while. Now it's is not. So I would not advise to do experiments on this, because if you just do experiment on these data sets, you may get your paper rejected because people will complain it's not state of the art anymore. Basically, the accuracies are quite high, so you get the average of diagonal maybe around 90–95% in the current methods, and so it's really the performance is saturated. So the main confusion is here. So between here there is some, but here is the most of confusion between running and jogging, and there is a explanation for this confusion. It's maybe not so much to the method, but to the data, because when we collected this data set, so we didn't label it, so we asked people to run and to jog, and so the people were students, and some were more motivated, some were not so motivated. So some were sort of jogging when we asked them to run. So there is some uncertainty in the labels here. So probably I would be surprised to see 100% method doing 100% on this data. Anyway, so this was a useful data set for some time. However, so we need to move on, and so at this point maybe it's good to ask the question: so what actually is the human actions, and what do we want to recognize? So is it just the kinematics of the body, or is it more things? So here is, for example, if we just think about the kinematics and look at these examples, so all of them, they would be rotating the hand, okay, and maybe classifying these images as rotating the hand. This is a plausible classification, but maybe in reality we would like to have some other quite different labels for this, because the opening a door and like starting a car are 2 different actions. Okay, and what really is different for this action is not just the kinematics of the hand, but the whole objects around it. So objects are important. So, and even if objects are the same, sometimes the whole scene is very different. And so this is just examples showing that it's important not just to look at people, but also things around in the whole scene. Okay, so here's just fun, but also motivating why we think scenes are very important for action recognition. So here's a pantomime, and so eventually people will recognize what's going on, but this is hard. And why it's hard is exactly because of reason that we don't see the surroundings, we don't see the objects, we don't see context. So so actually there are two things. So one is there is some spatial context here, and also the longer, so that's how usually pantomime works. So the longer you look at this, you accumulate a temporal context, so you can better, even if you don't see the object, so you can reason about what was before, what's coming after. So have any ideas? What is this? So he's a criminal, so he's going to rob something. And so I think this is quite distinct spatial context, which is supposed to be useful. Okay, so we want so this actually this is a counterexample which shows that just kinematics, from kinematics you can get the actions, but well, it also shows that it's very hard. So we are not used to see pantomime. Usually we observe the actions in real scenes, and this is what is very important. Also, what is now accepted, but it's was a step to move on from simple stage data sets to real world and to address this type of more complex scenarios, because probably if we keep working on these simple data sets, it will be very hard to move here. So there is a critics that the gap between this and this is very high, very large, and this is true. So it would be good to find something intermediate, and maybe some more restricted setups like sports, or maybe some observations in some, I don't know, patients or clinical setups. Maybe there could be some interesting application related and less wild setups where we could maybe develop better methods for action recognition, because currently this is still very, very challenging. Yet, so this is maybe one of the first attempts to address the real, I should not say unstaged data, because this is still staged. This is a movie, so it was staged, but it is played by real actors, not by students. So we imagine they should do their job good. So this is a nice movie, Coffee and Cigarettes, and was good for us because it contained lots of so people there sit and chat, and so there are lots of drinking and smoking actions. Okay, so we annotated people drinking and smoking. So annotation was by spatial annotation of the person, and also the extent, so when the person starts drinking and ends drinking. So this is the data, how it looks like, and so you see there are lots of variations here. So we have different people, different objects, and different viewpoints, lighting, so lots of things changes. So this is a nice real data to work on. So here the first attempt to address this data was to try to apply kind of object recognition methods to this type of data. So where our objects now are not just 2D motorcycles or bicycles. So here we have an action. So we cut out the 3D volume of data and compute some features, which are again optical flow and gradient features, which I've shown before. So we compute them in the bounding box, and so then apply some classifiers to it. So So if you are familiar with face detection, so here is other boost face detection. So here is an analogy to it. So instead of faces, we have now a piece of data which we describe with some histograms of motion and gradients. And so this is the other boost classifier which we train to select the boxes, and also so features are the boxes, and also H are the weak classifiers, which is basically it's a threshold surface in a feature space. So here is a histograms corresponding to features for positive and negative examples. So we search for a classifier which separates positive and negatives, and then so for each feature, and then combine them into a strong classifier here. Okay, and so what was interesting here, so was because of course given these frames, so you can also recognize actions by just looking at a single frame. You don't need video as a person. So it was interesting to see how these two information coming from the video and motion and information coming from single frames, how they complement each other. So we also trained the classifier which worked just on the key frame. Okay, and here the method was the same, but the features were not motion features in space-time. They were just features in static images. Okay, so the classifier was the same. And so the way how two classifiers, the space-time classifier and the static classifier, how was it combined? It was, so we've used the static classifier as a pre-processing step to just give us a hint where the action may happen. So these are results of running this 2D classifier over our training images. And so these are positives, but also it fires on lots of negatives. And then we use these negatives to feed into the space-time classifier as a second stage to get better results. So basically, so we have two stages. First, running the spatial classifier, just the static classifier, to remove lots of potential false positives, and then train and apply testing space-time classifier just on these pruned hypotheses. Okay, and this so this is training in the tests, how it works. Again, just running the static classifier here, and then checking this hypothesis with a space-time classifier. So you see here, so there we have lots of response for drinking, and we can eliminate the rest. Okay, so this is an example of a test episode. So the test episode was about 25 minutes maybe, so where we detect drinking people, and we can localize spatially and temporally. We can localize these actions. So the data set is online. So, well, not the movie. Movie you have to buy the DVD if you want to work on it, but we have the annotations online, so it's quite easy to. So some people try to replicate these results. So what method does here? So we see different people and different viewpoints. And also potential false positives. So this person is now going to phone. So it's sort of similar action to drinking, so but it's not recognized as drinking. Okay, so that was a good experience. So here is a 20. So it now, if we in the detection task usually, so we compute precision recall curves. So we take all the detections and then we score them by the confidence. And here are the 20 most confidence detections. So we see that it's not always as good because we have many yellows. Yellows are good ones, but there are quite many false positives still. So like these two guys, they're checking the watch. And so there are some smokings. So I think this guy is smoking, which is a very confusing motion. And this guy is drinking, and so he's red because he was missed in the annotation, but our method found it. So at least in one example, the method was better than the person. Fine. So here are some curves. Okay, I'm not. Basically, it turns out that if we just run the pure space-time classifier, the performance is quite poor. So the combination, so these two curves They correspond to combining the static keyframe classifier and the space-time classifier together. So they seem to really complement each other. So we get much better performance if combining them. So, okay, so what's the advantage of movie data? The movies are great because they contain lots of variability in the data in terms of viewpoint, different actors, so all variation you want. So it is there, maybe even too much variation. But the problem is that there are, so in the coffee and cigarettes, there were just many actions of drinking and smoking. It was good data set. But if you take actions like getting out of the door or answering phone, there are usually only very few samples of these in one movie. So we have a problem of data collection. And so to address this problem, so we can look at additional annotation. So people have been using additional annotation, for example, in terms of collecting images from Google image search, right? So if you want to collect, if you want to train a bicycle classifier, you can just type bicycle in Google, get lots of images, filter them manually. So this will help you data collection. So we've tried this with YouTube. With YouTube, it's quite difficult. So it's this is the real. This shows also the real problem. So currently, searching for objects or for video for events in video is very hard. So this is not reliable. So another way to address this without hiring lots of people to do annotation is to use additional data in terms of scripts. So luckily, so there is lots of TV scripts or movie scripts online. So here is one example from Casablanca, and there are hundreds of really movies which are with the scripts online. So what is a script? So it's not just subtitles. So it includes subtitles, basically subtitles what the people say, but it also has annotation of who is talking and eventually what is going on. For example, Rick sits down with Ilse. Okay, and so this information could be very useful for annotating actions. Okay, so if we can align this script with the video track, okay, for training, we can, if we know the timestamps of this in the video, we can just search by keywords. If you're interested in sit-down action, we can keyword search sit-down, then grab the piece of video corresponding to this, and then train a classifier. Okay, so we don't need any manual annotation at all. So this is very nice. So unfortunately, this type of data is not aligned. So if you just download the scripts from this, well, it turns out that the scripts are just not aligned. They are not temporally aligned with the video track. So to do temporal alignment, so it is a still open problem, how to do it well. So one trick, not optimal, but which buys us a lot, is to also download subtitles or get them from DVD. And advantage that subtitles, they do have timestamps because they have to appear at the right place, the right time on the screen, right? So they are very well aligned with the video track. Now, so because subtitles, so this is what people say. So scripts also have these parts, what people say. We can text align subtitles in the movie and subtitles, and transfer, after alignment, we can transfer the time information to the scripts. So this is a trick. It works reasonably well. So it won't work very good. For example, if people don't talk for a long while, then maybe lots of events happen. But so we will have very large uncertainty in the estimation. Okay, so script-based action annotation. So there are good things. So as I said, so we have access to lots of real examples of actions, many examples per class. So once we align the scripts and the video, so the annotation of new actions is very simple. We just do keyword search and we get new examples. But it's not optimal. So why is not optimal? So there is no, scripts provide no spatial localization. So actually you don't know, for example, where. So before we were annotating the drinking very specifically. So this person is drinking. So scripts won't provide this information. Temporal localization may be very poor. as I said. So there might be missing actions because scripts don't mention everything. So it's actually, we have on the actions which we looked at, so scripts mention about 30% of the content. So it means that 70% of actions we are not capturing. This is okay for training, more or less, because we are just interested in positive examples. If we don't have enough, we just get more movies, but it can be a problem. Okay, and so one more problem with the scripts is that it's not, even if you do keyword search, so it won't be optimal because it's scripts are natural language, so it won't always match to the simple keyword search. So here is an illustration of, just if you look at this image, so this is illustration of one problem. So a script says that the black car pulls up and two army officers get out. So we see here that indeed looks like one officer gets out, but we don't see actually the action which has happened here. So this is for us it's a good script, but it's not a good visual example to train a classifier problem. So another problem is the variability in text, as I mentioned. So it's we know variability in vision is very hard, but so we tend to think that text is easy, but text is also hard. So if the action get out of the car can be said in many different ways. And well, so basically if you run the keyword search, so you won't get many examples here. So here what we see are two precision recall, not points, type of points, not the curves points, for different types of actions. And so this the left plot corresponds to action retrieval in text, not in video, just in text by keyword search. So if we search for get out of the car, so we get quite low recall and precision here. There are some actions like kissing, so this is very, very good because kiss is a very discriminative word, but other actions are quite have lots of variability in the text. So if we, how we can improve this, we can actually go and label some text episodes in the script manually, and then train a text classifier, and then the results get much better. Okay, so this part was about trying to get annotation. So these are not visual results. This is just trying to get annotation. Fine, and so with this method, so we can collect now automatically lots of video examples. So we have in the latest data set, we have 12 action classes, and here are some examples of it. So answer phone, get out of the car. Okay, so the data set is online. So if you want to test on it, so this is not the only one. So there are now currently several data sets. In particular, was I think last CVPR there was this ICCV probably was a new big data sets also from movies, which has even more samples. But this is one of the current data sets where people test the recognition performance. So now for the classification. So again, so this is the bag of fish approach, which we can run. And so this is what it gives. So here is a demo of classification. So this is not detection, this is just classification. So whenever you see the red label appearing here, so it's the computer is answering a question, which action is this clip belong to. Okay, so this is was stand up, this is sit down. So what you also see is, so in yellow you see the script text. Okay, so like he gets up. So this script text is not used in the test, so it's just here to show what type of information we would be using if this would be the training data. Okay. So again, the variability is large, again with lighting, as we see here. So it's fine. So we have done some evaluation of this framework, and since they've been introduced many different descriptors, detectors, data sets, so it was hard to actually get a sense of what is doing what performance different methods are getting on different data sets. So this we tried to do a systematic evaluation of different methods for feature detector and feature descriptors on different data sets. So the baseline was again the same, was bag of words, and so we experimented with different types of features and different types of data sets. So the 4 types of detectors was the Harris 3D, which I described. And there were 2 more interest point detectors in space-time of these 2 papers, and also was a dense sampling, basically taking all the patches from the video. And the 4 descriptors, these are Hogg-Hoff descriptors, which I described, cuboid descriptor, this is PCA, something on spatio-temporal gradients. I think so. This is a spatio-temporal. This is a histogram of spatio-temporal gradient, and this is another descriptor, which was sort of coming from extension of another spatial descriptor, fast spatial descriptor. So to have a sense what are these points are in real images, so here are some the same sequence and 4 different detectors. So this is Harris 3D. So this is cuboid. You see that here actually gets more points, but single scale. And this is the Hessian. Okay, so this is a dense detector. So we don't see any changes because it's a regular sample patches. Fine. So the data sets was KTH data set. So it has many videos, but simple setups. So it was a more sport-oriented data set, UCF, where maybe it has not so many examples, but has real TV data. So the videos were collected from real TV data, and the Hollywood data set, which I described. So it was collected automatically or semi-automatically. So results were interesting in a sense that, okay, so for the simple data set, so we observed that the sparse detector, so we observed that the main result that the dense detector didn't do very well. So the sparse detectors were doing quite good, all of them. And so the difference in different descriptors, so Hogg has no motion, so motion obviously was important. So using motion was definitely important. And otherwise, so Hogg 3D was slightly worse than optical flow histograms. And so in terms of other detectors, so Harris 3D was better here, but maybe the differences were not so drastic, so maybe like a few percents. So this suggests maybe that, conclusions later. So for now, going for more complex data sets, so the results were different. So results shows that the dense descriptors were better, and also for Hollywood too. So we see that results changed for, so the dense descriptors basically were doing better. So this suggests that, so this observation has been made also for image classification. So like picking up the sparse points from the images for classification, for maybe for matching and for other tasks, maybe it still works better, but for classification tasks, it seems better just to sample as many patches as one can. And for video, it's quite demanding because if you sample all the patches in video in space and time, it generates lots and lots of data. So you have a problem of managing all this data. But so if you can do it, so actually you can get some boost in performance. So it's, this is good. And however, so the differences are also not that huge. And actually, in the practical, which we are going to do in next hour, so you are going to get this number or something close to it. So using these features and these descriptors, so you will get home a baseline which you can improve later on if you want. Okay, so what's the conclusion here is that so dense descriptors are better for realistic data, and why? Probably because it also captures not just well, it captures more. Probably it captures things in the background, for example, so which which is static, and the hardest 3D points would not capture. So. Fine. So since this simulation, there's been some development. So this was done in 2009. In last year, CVPR, so from Inria Liar, Cordelia Schmidt, so they proposed a new descriptor which improves. So I'll show the numbers. So, but what's the novelty in this descriptor? So it not just looks at the patches, it looks at the descriptors along trajectories. Okay, so instead of just looking at spatial-temporal neighborhood, so they are extracting what they call dense trajectories. So these are point tracks which are densely sampled in the image. Okay, and of course, you know, so these low-level tracks, they behave quite nasty sometimes. So they break and they restart again. So what to make methods robust to this behavior? So they cut these trajectories, I think, to 15 frames. So basically, so they sample trajectories in time, but keeping the length fixed, and then compute descriptors along trajectories. So this is one difference, and another difference that apart from optical flow histogram, so this is like 2 frames, and this is optical flow for them. So what Hoff descriptors does, compute histogram for this, and this would be the gradient, so we can standard descriptors compute histogram for gradient information. So they also compute information from motion boundaries. So motion boundaries are interesting. So this is, you can say, it's a subset of gradient, of image gradients, but which correspond to really, which often indicate the occlusion and disocclusion between objects and background, for example. So these carry additional information. So I think what happens that they take the optical flow image and then compute the gradient on the optical flow image, and then so this would be the gradient of optical flow in x and y. And basically what this is acceleration, right? So the optical flow is velocity, this would be the acceleration. And then make histogram of this. Okay, so this is additional descriptor called MBH. And the numbers are, so it doesn't improve by like hugely, but it improves consistently. So they show it on 4 different data sets, and they show a consistent improvement for, so like if they take Hoff and then motion boundary histogram, and if they combine all the 3 together, so they get improvement in all of them. So trajectory, the first line, this is a descriptor we just computed from the shape of trajectory without looking at the pixels around, so just looking at the shape of trajectories. And okay, so the improvement also good compared to state of the art. So they get on YouTube, on the complex data set, YouTube, Hollywood, and UCF, they have this. So this is a good descriptor. So if you want, it's also a good starting point. So they have a code online, so you can use. Fine. So so if you want to get somewhere further bag of words, so one can think of trying to merge bag of words with some higher level representations of one obvious idea one can come up with is why not to try to combine person detection and bag of words representation, because finally we are looking at actions of people, so why we're just taking this bag of words over the full frame. So let's try to look what this does. So say we can either run the automatic person detector, or even better, to have a baseline, we can even annotate the bounding boxes of people and see what's the best combination of this information with a bag of words. So here's one attempt. So here's the bounding box of a person. So say one way to combine the person detection and bag of words is just to say we assume that everything around the person is just distractors. So we want to remove these features in the background and just focus on the features on the person. Okay, so that's one way, and maybe also you want to do some kind of spatial binning to say that these features come from the lower part of the body, and these features come from the upper part of the body. So we can divide the bounding box of a person into a grid and collect features there. Okay, so what we see here, so here are the results. On the x-axis, this is the spatial tiling, so this is the amount of grids which we put. Okay, so example like 2 would be 2 by 2, 4 would be 4 by 4. And okay, this is the average accuracy on different data sets. So now the blue and red curves, so the curves with different color. So what this is, so the red is the bag-of-word baseline, and the blue is results which are obtained for combining person detector and bag-of-words, so what I described. Okay, so basically computing bag-of-words just on the person, not on the background. So what you see here is, so for KTH it works quite good. So now moving to UCF, so we see that it works less good, or it doesn't improve much. So now here we see the green curve, which is basically, okay, so the blue curve is the person detected automatically, and the green curve is person manually annotated, okay. So if we manually annotate the person and we compute the bag-of-words just in the person, we see a slight improvement as we go on with the tiling. Not very much. So this was now for Hollywood, it was even less good. So first we see that if you run the automatic person detector, so it drops a lot. So this is the bag-of-words baseline. So if you run automatic person detector and apply to it, so this is really performs much worse. So this is probably because person detection is still a hard problem, so we don't get it very good. But now if we manually annotate the people in the video and run this method, so surprisingly, so it's still, the green curve is still very low. So it's still below the simple bag-of-words baseline. So what this shows that things which one thinks should improve, not necessarily improve. So it's so even with additional information where we provide where is the location of the person, so it's easy to get results worse than one expect. Okay, why is it worse? So it's probably because we are removing lots of information from background, which is actually helping for the baseline a lot. Okay, so another attempt for improvement was to separate the scene into different regions. So not to focus on a person, but try just to separate the scene in different regions, which may have different semantic meaning. So here is one intuition. So for example, if we have a method, some method which segments the scene into different regions, so like error, R1, R2, R3, and with different meanings. So for example, R2 is a road, this is a parking lot. Then we can expect that features appearing here and features appear here, they correspond to different events, because here cars are running and here maybe people are getting out and doing different things. So maybe the intuition is that maybe we don't want to confuse this type of events with this type of events. So given this segmentation, we can separate, we can compute bag-of-words for this type, for different types of regions. Okay? And hopefully this should improve. And so what is the segmentation? So we don't want to commit. We don't want to some particular segmentation. So we try just different segmentation and see what works. So the simplest way of segmenting is just tiling the full video. So we can, like in spatial pyramid for image classification, we can just put the different grids on the full video and collect the features from the bottom, from the middle, from the top of the video. And this we've seen that in previous work that this has improved results. But this is a fixed. This is not dependent on the video itself. So what we want to have some segmentation which is image dependent and which is carries additional information. So here is another type of possible segmentation. So we download images for different actions from Google, and just train Pedro Felsenswalb object detector. We run the object detector over all the frames and declare that wherever it fires, so we declare this as a rectangular region, and we collect bag of feature representation in it. Okay, so we can do it for these action classes. We can also do it for object classes like cars and people. So we can, for each type of detector, we can collect histograms and then concatenate them into representation. And then once we have this, okay, so here is really the difference. So once we have different regions, we can separate it into bag of words and then concatenate into one representation, and then run the standard SVM. So what we get here, so this is the baseline. Here is so the spatial temporal gridding without taking image information into consideration, and then if we apply all the possible detectors, so we get better performance. Okay, so this is how to inject more information. For example, if we can train say action or object detector on a separate set of data, we can combine it with a bag of words and get some better performance. Okay, so so this is work which we also did 2 years back. So the intuition of this work is to combine action recognition with a scene analysis. Okay, so why is it interesting? Because so if we are looking for actions like eating, so they are maybe more likely to happen in kitchens or in cafes because of this just typical conventions. So people have dedicated places where they eat, or physical constraints apply for running, for example, because it's harder to run inside than outside. So we are more expecting running actions to happen in the streets or on the roads. So so there are two things. So one is that we want to capture this correlation and make it helping the recognition of actions. Another thing is that we want to maybe discover. We don't want to annotate and this correlation, but we want to discover it automatically. So one way to discover it is, again, looking into scripts. So we've used for action annotation, we've used this part of the scripts which eventually describe what people are doing. So there are more information in scripts. So there is quite structured information about the scenes. So for example, here's a Rick's Cafe Night. So this says where the actions are happening. Again, this is natural text, but it's it's even easier to cluster. So we can automatically discover the scene classes from this data and using some. So here some examples of this type of scene descriptions. So it mentioned restaurants and streets and so on. So we do some not very sophisticated text processing using WordNet and some other stuff to come up with a short list or long list of potential scenes in this data. Now we are not interested in all scenes. We are only interested in scenes which are correlated with actions, and this can be found because we have action annotation in the scripts. We are working with the same scripts, so we can measure the correlation of particular action which we have used already before for training and scenes which we discovered here. And so this is the correlation which can measure automatically. For example, for the scene office, so we can measure the correlation of this scene with our 12 set of actions, and we see that in the office, people answer phone, handshake, sit down, and stand up, which is which makes sense. And so this was discovered automatically, so we didn't have to do any annotation for this. Okay, so now so the correlation seems good, but this is only in text. So it would be also good that to use this correlation, it would be good that text-based correlation corresponds actually to the correlation which is found in video. So at this moment we don't know this because even if the scripts describe the video, the correlation might be different. So here's a plot which shows that it's actually correlation in its script and in the video is similar. So what we see here are so the size of the blob is the correlation, and the yellow-green is the part. The yellow part corresponds to the video, and green to the text. Okay, so text correlation means that's what I described, and yellow comes from the actually annotating the actions in video and scenes in video and measuring the correlation from the visual domain. Okay. So because these circles, they're about half-half divided, so this says that the correlation in text and in the video is similar. So we can use actually text correlation and directly apply it to video. Okay, so here is the data set. So the action data set is the same as before, and here we have 10 scene classes. Automatically labeled from the data, from the scripts. So before the joint framework, so we also checked how different descriptors perform on this data separately. So here are SIFT, so static SIFT, this is Hoch-Hoff descriptors, and these are all combined. And so this is a separate relation, which is interesting. So what features are better for which classes? Okay, and so the presentation is the following. So the classes have been sorted such that the classes at the left are better recognized with SIFT, so with static features, and classes at the right are better recognized with dynamic features, which are Hoch-Hoff. Okay, the red bars are higher here, and the blue bars are higher here. And here are all the classes, both scenes and actions. So what is interesting to observe here is that we have mostly the scene classes mostly appear here. So office, road, bedroom. Okay, so scenes are better to recognize with the SIFTs, with static features. And here we have mostly action classes like sit down, drive car, fight person. So these are the actions which are better recognized with dynamic features. So there is one exception. So enter your car is fires very good with dynamic features, and this is probably because of the motion in the window. So when we have a driving scene, then there is lots of motion in it. So this is natural. So also it's quite usual that when you combine descriptors, so performance goes up a little bit. So that's what we see. So if we combine the SIFTs and the space-time descriptors together, so on average we get a little bit better, well, some better results for scenes, and also slightly better results for actions. Okay, so the combination of descriptors works. Now, if you want to, the next experiment is to help scenes to improve action recognition. So the model here is quite simple. So it's a linear perceptron kind of model. So we have scores of which we obtain from the scene classifier and scores which we obtain from action classifier. And now W's are the posterior probabilities of a scene given an action. So this is sort of our glue, how to glue together the performance of action classifiers and scene classifiers together. And so what we observe is that so if we combine action recognition with scenes, so we can observe up to 10% in average precision for some actions, and on average maybe it's about 3%. But there are actions which benefit a lot from scene information. So what is interesting that we can convert the problem and try to improve also scene classification by action recognition. Actually, the improvements are very similar. So we get at most 10% for some scene categories, like road and living room, for example, by action classification. Okay, so I've talked about action classification quite a lot. So I'm going to talk also about the last part. I'm going to talk about action localization. So not just answering the question what has happened, but also when the action has happened. And again, we want to keep being in this semi-supervised setup or weakly supervised setup where not all the annotation, not exact, all exact annotation is given at the training time. So we are going to use scripts again. So we could actually run it in a very large scale by just analyzing the scripts and so parsing the scripts and finding the reoccurring expression, for example, like person plus verb plus person plus verb preposition, so on. And we see here that by doing this, we could get so all the reds are manually marked as a potentially interesting action classes. So we could, in this way, define automatically lots of different action classes. So this, however, the problem with this approach would be the evaluation, because even if you could train the system completely automatically on lots of different classes, it would be still hard to evaluate, because for the test we need the manual annotation. So then this work was finally still on very few, actually 2 action classes, which was open door and sit down. But the problem which we faced was to address the temporal uncertainty in the annotation. So I've mentioned that if we use the scripts, which are great, which provide additional information, they have drawbacks, and one of them is that we don't know exactly when the action has happened. So if the temporal localization is provided by subtitles here, and this may be very imprecise. So to address this problem, so here is an overview of the method. So here the input was the videos aligned with the scripts and some action type, for example, person open door. And here we just did keyword search for open door to get the initial samples. Now the problem is that the samples which we get from script, they can be quite large, so usually like 1,000 maybe frames. And okay, the problem is following that, so these are temporal extents of the clips which we get, and we know that there are open door action is somewhere inside there, but we don't know where it is. And all the blue is potential noise, which we would like to remove. Okay, so at the training time, so we would like to cluster together the all the actions and remove all the noise. Okay, so this is the motivation. And okay, we want to do it automatically without any additional annotation. Okay. So action clustering. So it has been addressed before. It has been shown to work very well, very nicely, but in quite simple setups where background is static. So we have defined simple sets of actions. And so one way to do it, okay, some generative methods, for example, can do clustering, like spectral clustering, for example. So here is a similarity matrix of all-to-all frames. So if one does spectral clustering on this, so one can see the nice clusters pops up. So basically by getting different, well, basically, if the data already clusters in the feature space, then the generative clustering works good, and that's it. Okay, now if the data is more complicated like this, so there are many problems. One problem is that probably these actions themselves, they are quite spread in the feature space because they look very differently, but also we have lots and lots of background noise, which makes the problem even harder. Okay. So the standard clustering don't work. So here is how to, another way how to see the problem. So say we have a video track, okay, here, extracted by the scripts, and we also have a action here. So we don't know the temporal position of this action, but we know it's somewhere there. So in the feature space, this would be trajectory. So this is time dimension. So it would be trajectory, and the red would be correspond to the action. Okay. So if what we can do, we can slide the window along the time, and this would correspond to sliding the point along this trajectory. So if we have several examples of clips which contain the action, so this will be several tracks, and what we know is that each of them should contain at least one red cross, but we don't know where it is. Now, thinking of back to generative methods, so what generative methods would do, they would try to find something most common between all these tracks. And maybe this could be something like this. And so this is just schematic. This is not real data. This is just schematic representation why it may fail, because actually the actions might be spread quite a lot. So how to deal with this problem? So we don't want to annotate any more information. So the way to deal with this problem is the following: is to remember that we not only have there is more information which we have not used so far, and the more information comes from negative samples. Okay, so we don't know anymore. We cannot get more information about positives, but actually we can get information from negatives. And negatives are good because they are very cheap, so we can just sample randomly the videos and hope if the action is very rare in this data, so we can hope that all these points are really negative. Eventually, this could be positives in the negative data, but because they're so rare, so we hope to be robust to it. So what the negative data says, so it says that at this part of trajectory, so we are not expecting to see any positives. So this is what's going on. And also what we know experimentally. So if we annotate the red crosses, and if we take the blues negatives, we know that we can train a reasonable SVM classifier which separate the reds from blues. Now, the problem is that we don't have the red crosses, so we want to discover them at the same time and learn the boundary, the decision boundary. So mathematically, so it's formulated so as a SVM loss as follows. So if you're familiar with SVM loss, so this is this is very standard SVM loss, with one exception that for negative data, it's exactly the standard as linear SVM here. So we see x this f of x minus this is the feature of the negative training sample. So now the only difference is that for positives, so we parameterize the positive samples by the position. So Fi is the position of the sample on the trajectory. Okay, so there is a one-dimensional uncertainty in this formula. So now, if you would not have this, if you would fix Fi, so we could run the standard SVM, and we could solve for W and the B. So these are the parameters of SVM, which will provide the boundary. So that's what we do. But problem is that we have to fix Fi. So this becomes linear SVM is a convex problem. However, if with this parameter, so it's not convex anymore, so it cannot be solved optimally. And the trick is, which is used in many methods now, so is to iterate, to fix the Fi, solve the SVM, and then by fixing the W and B, to optimize over Fi and to iterate. Okay, so this is a iterative process which is now found in many cases. Okay, and this way, by running this procedure, we end up with some. So it's what converged to the optimal solution, but in practice we observe, so it converged to interesting solution. So here are some examples. So coffee and cigarettes. So say the blues are the okay. So each line on this plot is one clip, and the blue corresponds to a particular position of the drinking action in the clip. And so what we are able, so the red ones are FIs, so in the previous formal, these are FIs which are trying to localize the action in the training. So we see most of them, they are correct, few of them are wrong, but most of them they are converged to correct positions. So this is a illustration that the method does work. So here, okay, maybe skipping to okay, maybe just explaining this. So if we would use, now we can think of action detection using either training representation from the whole clip or only from the actions which have been localized with our method. So these are sort of two different approaches. So this would be the baseline. So if we just take the information from the script, so it will be a large chunk of data, we compute bag-of-word representation for it, run a classifier, and okay, so this measure performance. So this is a baseline, but the problem is that it will contain lots of noise in the training. So hopefully better method is we restrict to points where we have actions and train only from them. So that's what we see, the improvement we see on this curve versus this is exactly this. So by automatically localizing actions in the training, we are able to learn the better classifier. And here are some results, more results for other movies. So we have sit down and open door action. So this is a baseline similar here. So this is the baseline where we train on the big clip, on the large clip provided by the text. So it's quite low. So if we are running automatic clustering method during training stage and apply the classifier at the test stage, so we get the red curve. And the blue curve is actually the ideal segmentation of actions in the training, which is done manually. So we see that the automatic method is, in terms of performance of action detection, is not very far from the manual annotation. However, so the overall numbers are still quite low, so there is lots of room for improvement here. And so, nevertheless, so as usual, so after some work, you can make a demo which works nicely. So here is now a detection demo. So where we make computer look through three movies, or maybe six. Yeah, no, it's 3 movies, and stop. So it's a sort of intelligent fast forward, and to stop whenever the open door or sit down action happens. So we are not claiming we are solving the task. However, the variation in the data is quite large. So we see the glass doors and this type of many type of okay, so I'm almost done. So some conclusions. So I'm not claiming bag of words is the best method ever, but currently it does well on the benchmarks. And so if you are going to develop your own method, so this is a bag of words as well, is the method which you should try to compare to. However, of course, in bag of words, lots of problems, and one of the problems is that it doesn't capture, as in the images, it doesn't capture the structure, so in the space or also in time, so the structure is very loose at the moment. You would like to reason much more about so what happens first, what happens after, and also potentially incorporate for example, the poses, human poses, and together. So this is still, and as you've seen, also the performance on the very challenging problems, so the performance is still quite low, so there is lots of room for improvement. However, even beyond this, so there are things which are conceptually even more difficult. So what is vocabulary of human actions? So currently we just pick up some few classes of actions, but it's not clear that this is actually the classes which we want at the end, because if you are finally want to solve some particular task, then the vocabulary of actions, the optimal vocabulary of actions might be very different. Okay, and I want to conclude with some thoughts. So what is beyond action recognition, or maybe more how action recognition is related to other tasks in computer vision. And so if you look at other tasks in computer vision, so say, for example, this is a scene you want to analyze. And so with all previous years of training object detectors or scene segmentation, so say we can pretty good, by using lots of training data, we can pretty good learn classifier which would say that this is a car, this is a street sign, this is a road, and so on. Okay, so this is a more or less problem which is getting solved. So however, so is this the final output which we would like to have from our visual system? Okay, so say in object recognition, so what are the next challenges? So people now, after Pascal, so people go to ImageNet, and this is a great effort. So now we have over 17,000 different categories and 12 million images, lots of data, so we can train lots of object categories from this. So if you see this object, I didn't know how this object is called since very recently, and however, and this is one of the objects in the ImageNet. Okay, so what I'm trying to say that even if I didn't know that what this object is, it was no problem for me to use this object. And why I knew how to use this object is because I probably was at a similar place before. I've seen what people are using with this object. And that's my internal definition of this object. So I don't need the label of it actually to do something useful with it. Okay, and also in this scene, so maybe labeling the scene by cars and by different labels is good. But if I want to grab a taxi there, or if I'm a robot who wants to grab a taxi there, then what is important is not to label this as a cars, but to know that if I'm going to run there, then maybe these cars are going to hit me. So it seems what is, even if we are trying to get better and better in object recognition, so it seems what is missing is some functional description of the scene. So what we can do with our object, how will scene react to my actions, what can happen in the scene. Okay. So here is one image. Okay, so if you run Pascal detector, Pascal airplane detector, maybe a good detector will put the bounding box here. So this would be great, but maybe this is we maybe want much more of this from this image. We want explanation that something unusual has happened. So it's not usual to see the airplane on the street. So maybe there is this. Well, we want maybe a system which automatically would alert that this is an unusual situation. Again, this example with the cat. Okay, so currently, so we can detect cats, trash bins, and maybe put bounding boxes, segment them. So still, it won't bring us very much closer to that. This is a very untypical situation. Okay. So what I think in the future where we should be looking at is maybe try to move from labeling the objects, or maybe this is the point of convergence between the action recognition and object recognition, where we should stop, or maybe not stop, but go beyond just labeling actions, labeling objects, but address the more difficult tasks of answering questions like what can I do with an object, or what an object can be used for, or predict, so what can happen in the scene. So given the current state of the scene, what can happen in it? And eventually also recognize the goal. So if we have, for example, a picture of a person running after the bus, then it's important to know that, understand that the person is trying to catch the bus, for example. Okay, so this is it. Thank you very much. Okay, so this is a slide from the last hour. Okay, let's move on. Okay, so this is a dynamic. This is one of dynamic scenes, and say we want to interpret this scene. So all maybe what we've seen before. So I would say that it would have issues. The methods which we've seen before, it would be complicated to analyze such a dynamic scene because we have many problems. So what are the problems? So what are the common methods first? So first, maybe if you want to do shape analysis, so you would need to do some segmentation. So if you would need to track, so maybe the previous methods which you've seen, so tracking the person, analyzing the motion of the person. So again, tracking would have issues in the scene because of many things. So what are the problems? So for segmentation, we have a complex and changing background. So we just cannot segment the scene. So can you see? Can you see here something? It's maybe hard. Because the background is dynamic, everything is moving, so it's basically impossible to segment the scene. So why actually does it fail? Because usually segmentation methods, they have some model about the background. So they usually assume that the background is something static, big. So everything which is not moving as the background, this is a foreground. Okay, this is a typical assumption for segmentation. So here it just fails. Okay, so the assumption for tracking is that things are continuous over time. Okay, so that you have appearance. Maybe you have some model of appearance, how it changes. Maybe so the shape of a person and so on. But either you have a model or so assumption is that you know enough about the foreground so you can model it appropriately. Otherwise, the tracking will fail. Okay, so both two things are problematic because in realistic scenes like this, so it's hard to assume anything about the background, and it's also hard to assume things about the evolution of, say, person or other things over time, because the appearance may change drastically for the reasons which are hard to model. So all this, so if we still want to understand this scene, so maybe a reasonable way to deal with these problems is not to do any assumptions about the background of the scene and also about the temporal continuity of the signal. Okay, so we don't want to do any global assumptions in space, neither in time. Okay. So and now if you don't do any these global assumptions, so maybe what is left is just to look at local information, so which is available in the video. So say now, okay, we are back to simple sequence. It has a gradient, space-time gradients have different direction. Okay, and the same things happens here. So if this is a sort of example where some structure hits a wall or two structures merges, so we get these events. Okay. So it's not that other events are not interesting, but these are some distinct events which could be interesting for recognition. And now, now for real sequences, so we can get something like this, firings, and here's a football heading the ball, and so we get, so on the space-time slice, we can get an event which corresponds really to a space-time corner. Okay. So one can, as for other interests, so spatial interest point detectors, so one can make it scale invariant or scale covariant, so that if we have a camera zoom, if we have a variation in terms of the scale in spatial scale, so we can detect these points which so see they follow the scale. So why is it good? Because if we are going to compute some descriptors at this point, so we not just need the location, but we also need the size of the patch. Okay, so to make really two descriptors in different videos to correspond, not the corresponding central location is not enough. You also want to have the size of patches to correspond. Okay, so if you want to match this leg to this leg, then obviously we need to adapt the size of the descriptor. So in space-time, similar. So we also need to adapt the. We may want to adapt the temporal size of the descriptor. So what is temporal size? So here is a hand waving with different frequencies, and we see that the size of the temporal size of the blobs, detected blobs, it's adapted to the frequency of the event. Fine. Okay, so these are points which are detected for different types of actions. So here, as we've seen, this is boxing, this is hand waving, this is, you can guess probably what this is. What is this? Walking, yes. Okay, and now so we reduce the representation of these actions to a collection of patches. So this is a way to represent videos. So once we collected the patches, we also want to describe them. So one description would be just to collect the pixels and maybe do some contrast normalization. So it turns out practically better to make descriptors in terms of histograms. So as you well know, the SIFT descriptor is a histogram of gradients. So here we experimented with many different descriptors, and these are the ones which seems to work best. So it could be gradients of histograms of gradients, so spatial gradient orientation, and histograms of optical flow. So we collect the optical flow in space-time neighborhoods and quantize them into very coarse quantization. So just 4 bins of the for the upward, downward, left-right motion or no motion. This is the histogram. And also in a SIFT manner, so if this is the patch, so we divide it into a few blocks. Why is this useful? Because it preserves some spatial or temporal information, but is not committed to a very precise location. Okay. So here is one illustration of what the method is doing on simple sequences, and you will experiment with this example in the practical exercise in a short. So what happens here? So we first extract the points, and so we can we extract the points. We extract the patches and apply some descriptors to patches. We can next do standard k-means clustering on these patches and say extract the 4 clusters which are most common. And because the action is periodic, so the most common will correspond to repetitive, small repetitive structures. So if we just select the patches which correspond to the first 4 clusters, so we remove the noise, and also we can get the kind of semantical, although there is no in k-means, it's not a semantical method, but it does cluster similar events, local events together, so we can have a nice representation. And now if we keep this dictionary, okay, so if we keep these 4 clusters and we apply it now to a different sequence which has not been seen during the construction of this dictionary, so we can still recover the same type of events in the new video, okay. And now also here we start to see advantage of this method is because we have cars and things moving on the background, and the method is invariant to this type of variations. So here is another visualization why this approach could be useful. So here we have many videos, and we just try to do nearest neighbor matching between descriptors, so without taking into account any global information, so just based on the local descriptors. And so as you see here, there are quite meaningful matches here, so between different people in different situations. So we get quite good matches, so this would indicate detection. So how many of you know Harris point detection? Okay, quite many. So this is really very similar. So in the Harris point detection, so if you're familiar, so you have a 2x2 matrix which you analyze. And what is this matrix? Actually, this part of the matrix is the same matrix which we've seen in the previous hour for optic flow estimation. So it has many different names. So one name is is, so what is it called? This second moment matrix, yes, here it is. So basically it's a covariant matrix. So if you assume that the gradients have a zero mean, then so this matrix would be the covariance matrix of gradients in a local neighborhood of an image. Now if you extend it to a video, so if you have a spatiotemporal neighborhood, so the matrix become 3 by 3, so you just measure the gradient vectors are 3D, so this is a covariance matrix measuring 3D. Okay, so what Harris standard 2D Harris point detector does, so it tries to find points which have both eigenvalues large, eigenvalues of this matrix large. So why? Because the typical corners they would correspond to points where we have a gradient direction to different, well, in not just in one direction, but in many different directions. So that's, for example, why optical flow estimation would also work on corners, because we have gradients pointing in different directions. Okay, so similar thinking here. So if you have a if the rank of this matrix is 3, so this indicates some interesting space-time structure, which is maybe some corner which moves not only with constant direction, but also, so it has some significance in time, as it has some change in the motion in time. Okay, so maybe just simpler to show this with videos. Okay, so the form of the saliency function is like this. So it's about trace and determinant of this matrix, and so what basically, okay, I'm not going into details of this, but this function fires. If we maximize this function over space and time, then so it fires at this. For example, for the examples here in the videos, it will fire on blue points here, and so can you guess what? So is it clear what this shows? So basically, so this video and this picture, they correspond, right? So this is a corner which moves up and down, and so the firing. So this is a time dimension. This is x and y, and the firing is in particular point in time and in space, because it has a sort of a space-time corner. Basically. It says for illustrative reason. So if you just look at these simple sequences, if you take space-time cut on these sequences, and so again, this is not the data which we are going to analyze. This is just to visualize how the data looks like if we just put the threshold surface around the silhouette and stack the silhouettes in time. So that's how it looks like. And now we see already this with this visualization. So it's this shape, if you call this a shape in space-time, this looks very differently, not only in global, but also in local. So if you think of analyzing some local properties of these parts in space-time, so they seem to be quite informative. So of course, going this thinking is inspired by analysis of images. So in still images, maybe you are familiar with visual words representations, where you can first subdivide an image into patches. There are many different methods to do this, and then cluster the appearance of different patches, so that you not necessarily get semantically meaningful things, but quite often you get something which is quite consistent. So you get parts of airplanes and so on. Okay, and with this type of representation, so it has practically proven to be very useful for recognition. So if applying now similar strategy to video, so what we can do, we can think of now looking at local spatiotemporal neighborhoods around some particular points, or maybe even just taking all the spatiotemporal patches in the video. And now, as I said, so we are not looking at this green surface, but looking at spatiotemporal so representation, the pixels over space and time, so we can get the 3D patches. And now these 3D patches, which extracted here and here, they're really different. So imagine we can also, and similar to this type of presentation, so we can imagine we can build some classifier which just works on local patches and would be able to discriminate between these two actions. Okay, and the goal, of course, is to move on to more complex videos. So here are still a simple citation, but in more complex videos where we would have a complex background and so on. So if we are just reasoning about the local information, we should be less dependent on this variation which happens around the person in the whole scene. Fine. So this is okay. This is one possible way how to extract first the points or the spatiotemporal neighborhoods. So this is just one way, and there can be other ways. So the reasoning here is similar to Harry's point